Hello, good afternoon, and welcome to Chapter 5. We are getting close to the end of the semester here. And Chapter 5, we are going into a subject where we're tying in some geometry that we've learned, and we're going to call it trigonometry. So we're taking our geometry, we're going to put it onto our coordinate axes, and we're going to tie in angles and some other things. It's pretty exciting. So anyway, let's turn into our book here for a moment. There are a lot of definitions in this chapter, this lesson 5.1. So it's really important that you go through and take notes of everything for yourself, especially if you need to get reacquainted with some geometry things. So an angle is formed by rotating a ray or half line about its endpoint. The initial side of the angle is the starting position of the ray, and the terminal side of the angle is the final position of the ray after rotation. The vertex of the angle is the point about which the ray is rotated. So let's go to look at figure 1 and 2. We can see that our 0, 0 coordinate, if we call this our coordinate system here with our 4 quadrants, our vertex is our 0, 0 point. Our initial side is always going to be the positive x axis. Okay, that's going to be our initial side, and we're going to go to the left, and this angle is called theta, Theta. And we're going to call that angle theta, and then when it goes over into the second quadrant, that's called our terminal side there, where my arrow is. That's a positive. So when we go counterclockwise, it's considered a positive angle. Now, figure 2, it has to have the same initial side. Initial side is always when we start on the positive x-axis. Now, this initial side, it goes down, which is clockwise. That's going to be a negative angle. And then you can see where its terminal side here on this angle is in the 4th quadrant. Okay. So a positive angle in standard position is generated counterclockwise, and a negative angle is generated clockwise. Okay, so you can see that here, the angle that we drew in figure 1, now down here in the left of figure 3, was actually a 130-degree angle, because if we take a circle, which is 360 degrees, and we divide it by 4, each quadrant has 90 degrees in that quadrant. And then the angle that we drew up here in figure 2, where we went clockwise, they draw it down here at the bottom right in figure 3, and that was a negative 35-degree angle. Okay. And we're going to go back and remind ourselves some things as well. So a right angle is an angle that has 90 degrees. A straight line or a straight angle has 180 degrees. An acute angle is an angle that's less than 90, so it's greater than 0 but less than 90. And an obtuse angle is any angle that is greater than 90 but less than 180. And there are examples here on page 404 of those. Again, I recommend taking some notes. So I'd like to look at questions 9, 11, and 17. It's asking us to sketch the angle in standard position. So before we move on to more definitions, let's go ahead and practice drawing some angles. Okay. So the first angle we want to draw in standard position is this angle of 135 degrees. And so we are going to start here. And we said that our it's in standard position as long as its initial side is here on the x-axis. And we're going to go, that's 90 degrees. And then we want to go into this second quadrant because that's where 135 is. And you can kind of get a feel for what that would be if you take 135 and subtract 90. And that means 45 degrees is how far it goes into the second quadrant. 45 is halfway into the second quadrant. So we would want to come out like this. So this angle is 135 degrees. Number 11 is asking us to go a negative 135 degrees. So we're starting here on our initial side as well. And this time we're going in the negative, or what we call the clockwise direction for this angle here, which is a negative 135 degrees. And then 17, they're giving us this, it's called in radians. We're going to learn about what a radian is momentarily on page 404, well, actually 406. But 9 pi over 4, we are, if we go to our, let's draw for ourselves just a quadrant system for a moment. And if we take and go all the way around and make a circle, that is 360 degrees, and my circle making is not good. And that's in degrees, but we also call this rotation, a full rotation is also equivalent to 2 pi in radians. Okay, 2 pi in radians, these are equivalent. So, and 1 pi in radian is over to where we would call the 180 degrees. And so 1 pi is at 180 degrees and 2 pi is a full circle. Okay, so they want to go 9/4 pi, which 9/4 pi means that we went, let's just rewrite this, 9/4 pi means that we went 4/4 pi, so a full pi plus another full pi, because that would be 8/4 plus 1/4 pi. So you can kind of break this down that we went 1 pi, 2 pi. So we've gone 2 pi plus 1/4 of a pi. So we're going to start here on our initial side, and we're going to go 2 pi, so all the way around, and then we're going to go 1/4 of the way right there. And 9/4 pi, if we take and we multiply, just take 9/4 and multiply by 180, times so you can see 9/4 is 2 1/4. So we went around once because that's 2 pi. And then 1/4 of the way, 1/4 of a pi would be right here. Because that's 1 pi. So 1 pi would be 1/4 of a pi. And then this is another 1/4 of a pi, and this is another 1/4 of a pi, and this is another 1/4 of a pi. So it went right here, which would be 9/4 times 180 would be 405 degrees. So if we subtract the 360 degrees, then this is the extra 45 that we were going to go. So 1/4 pi is equal to 45 degrees. Okay, The next ones that I wanted to look at were looking at what a radian is. So we talked about sketching an angle. Let's talk about coterminal angles. So coterminal angles, if we go back to our book here. Coterminal angles right here. Two angles that have the same initial and terminal sides are said to be coterminal. So we actually just went over coterminal angles, what we just did in number 17, because let's look at this example. We'll go back to our example. So it says for each angle, find two angles that are coterminal. So if we look at 135, right there it is. And then any other angle that goes around and ends at the same spot. So if you go a full 2 pi or another 360 degrees, you end up at a coterminal angle. So 135 plus 360 is 495. And likewise, you could do 135 plus 360 plus another 360, and that would be at 720 plus 135 would be 855. We can do the same way going clockwise in the negative direction. So let's go back to my paper, and I'm going to show you how number 17, we essentially found coterminal angles, because we said that 9/4 pi is all the way around plus an additional pi over 4. So pi over 4 is coterminal with 9 pi over 4. But let's look at a couple from the book here. And how about we look at 21? So 21 says 140 degrees. So 140 degrees is going to be over here somewhere. And so we could do it. It's asking us to find two angles that are coterminal. So we could do 140 plus 360. So that would be a 500 angle. And then we could do 140 plus 360 plus 360, which would actually be 860. So those are both coterminal because they go around and around and land there. Let's do one for number 30. So number 30 is asking us to find two angles that are coterminal with 3 pi over 4. So 3/4 of a pi. So we said that pi is right here. And so if we broke pi into quarters, this would be 1/4 here. This would be 2/4. This would be 3/4. This would be 4/4, which would be the full pi. So this is a 3/4 angle. And we said 3/4 would be 135 degrees is 3/4 pi. Okay, and so we could say 135 plus 360 is 495. That's one angle, but that means we are adding 2 pi to that. So if we want to write that as 3/4 pi plus 2 pi, and 2 pi is really the same as 8/4 pi. So that means 11/4 pi is a coterminal angle. And 3/4 pi plus 8/4 pi plus another 8/4 pi gets us to 19/4 pi. And that's another coterminal angle. Because every time you add 360 degrees or 2 pi, you're coming up with another coterminal angle. So let's look at number 35. That gives us one where we're looking at a positive and a negative coterminal angle. So 35 is a negative 65 degrees. And so we could draw that. That's going to be this way, so not quite to 90. So we could add 360 and find one that lands on the same terminal side. So negative 65 plus 360 would be 295. That's a positive angle. They wanted one that's positive and one that's negative. So we could say negative 65 and go in the same negative direction, 360. And that would be a negative 425 degrees. Okay. Now you might be saying to yourself, why in the heck do I care if it's positive or negative when they're actually coterminal with each other, because they just have to add to be 360. And that's because eventually we're going to turn this quadrant system into like a north, south, east, and west. And we're going to talk about flying and how you're going in a southern direction in a certain angle. So we're going to need to be able to talk about positive and negative angles for that purpose. Okay, let's talk about number 42 is the angle 33 degrees, and its complement angle means what is the angle when added to it gets me to 90. That's a complement. And so that would be the angle of 57. They're complements of each other. They add to 90. And then let's look at number 48. 48 is 112 degrees, and they wanted us to find the supplemental angle there. And that would be the angle when added to 112 gets me to 180. And that's going to be a 68 degree angle will get me to 180. And then, of course, we need to go back and kind of talk about radians, because we need to learn how to go back and forth between radians. So let's go just take a look here in our book at the definition of a radian. Okay. So in order to study trigonometry using functions, we measure angles with a unit called a radian. To define the radian measure, we will use the unit circle that has radius 1 and is centered at the origin, called the unit circle. Okay, so we're going to go back to a little piece that we left out back in chapter 2, talking about equations and functions of circles, because it's now necessary. We're going to go back and do that for chapter 5.2 when we introduce that. But we're using this unit circle where the radius is 1. So when the radius is 1, it says, for we can complete one counterclockwise revolution of the terminal side of an angle cuts off the entire circumference given by this. So we can say that the circumference of this circle here is equal to 2 pi r. 2 pi times your radius. Which essentially, if you can measure any circle, so let's say I wanted to measure any circle, if you took your radius and actually your diameter, and you took your circumference in relationship to your diameter as a ratio, circumference divided by diameter, you would always get the ratio of 3.14 approximately, which is pi. And so we are going to use that as the measure of the arc length. See where my mouse is here? It's the arc length, that measurement. And all the way around is called the arc length, which is the circumference of the circle. So we can see here at the bottom of page 406 that pi over 2 is the arc length between the x-axis and the vertical y-axis there. So it would be the coordinate point 0, 1. And then pi is all the way over at the point -1, 0. And then 3 pi over 2 is all the way around at the point 0, -1. And then 2 pi is the length of the arc that goes all the way around first full circle. So to convert, 1 radian is equal to 360 degrees divided by 2 pi, which is the same as 180 degrees divided by pi. And so 1 radian is approximately 57.296 degrees is 1 radian. So to go from angles, from converting angles from degrees to radians, we are going to multiply by pi over 180. So they give us some direction here. Oops. Pi over 180. Right here at the top of page 407 where my mouse is. So degrees to radians, you're going to multiply by pi over 180. And if you're going from radians to degrees, you're going to multiply by 180 over pi. So let's just look at a few here that we can get some idea on this. So number 53. And 61, they're asking us to go from degrees to radians. So let me go back and share my paper with you all here. So we're going from degrees to radians. So we're going to multiply by pi over 180. And what's cool is we like to keep it in terms of pi. So I really want to show you this in Desmos because it will, actually in my calculator, I should keep it in fraction form as well. It's nice to keep it in reduced fraction form. So 150 divided by 180, and then we should be able to go to alpha in the y equals, and we should be able to go to it'll be 5/6. If you reduce 150 over 180, it's 5/6. And it's a negative, so it's a negative 5/6 pi. So what that's saying, and it's nice to kind of keep practicing this, is if I take pi, which I know is 180 degrees, and I divide it by 6, every one of those 6 is 30 degrees, and I'm going to multiply times 5, which gets me to the 150. That's what that's saying. Number 61 is 360 degrees, and we want to turn that into radians. So again, we're going to do 390 divided by 180, and then we're going to do our shift. I'm sorry, our second key in y equals. Nope. Sorry, my alpha key in my y equals, and I'm going to choose number 4. If you're doing it in Desmos, it will also, there is a unit exchange. I will show you that here in a minute. And that is 13/6. So that's 13 pi over 6. So let me show you this in Desmos for those that are using Desmos so that you're comfortable doing it. So Desmos, if you were to do 150 divided by 180, it gives you the decimal. And then notice over here to the left, there's a little fraction in the circle, and you click on that and it puts it in a fraction. And just like the 390 divided by the 180, again, you can just click it and it puts in a fraction. It's a lot quicker than the calculator, actually. So let's look at going from radians to degrees. So I was thinking number 65 and 67. And how about we do 66 while we're at it, just for fun. Okay. Go back to my paper here. So we're going to look at 3 of these where we're going to transform from radians to degrees. So pi over 180. When we're going from radians to degrees, we're going to multiply by 180 over pi. And this just happens to cancel. And that's just 1 degree. That one was kind of boring. Let's look down at number 66. 66 says pi over 45. So again, we're going to multiply by 180 over 40 over pi. Over pi. The pi's cancel. So we're left with 180 divided by 45. And 180 divided by 45 is 4. And we've done a little bit of this already. Let's do number 67. So again, we're going to multiply by 180 over pi. So the pi's cancel. And we're going to say, I'm going to do the, this is a -2/5. So it's a -2/5 multiplied by 180. And that's going to be a -72 degrees. So you want whatever you're getting rid of, you want it to cancel that. So that's what's going to go in the denominator. Okay, let's look at some of the application problems. So let's look at number 69. Take it to the book here. So number 69 in the book says, it says, what is the angle swept out by the second hand of a clock in a 10-second interval? Express your answer in both degrees and radians. So 10-second interval. So if we think about what 10 seconds is out of a full revolution. Let's go back to our paper for a minute, so you can see how I'm thinking about this. So we have to think about what 10 seconds is. So if we think about 1 revolution of the clock, if we keep it in seconds, is going to be 60 seconds. So this went 10 of the 60 seconds. And they want us to put that in degrees. So 1/6 of the 360, right? So 10/60ths are 1/6. So we could put in parentheses 10 divided by 60, multiply by 360 means that we went 60 degrees. And then in radians, that means 60 degrees times pi over 180 is 60 divided by 180, which is 1/3. So that's pi over 3. Is number 69. So these definitely kind of challenge our thinking a little bit from what we've been working with. Let's look at number 73. Number 73. So we can read it together. Number 73 says it's geography. Earth makes one full rotation about its axis every 24 hours. How many degrees does the Earth rotate in 1 hour? Okay. So every 24 hours, it goes full rotation. Yes, it does. Pretty cool. Okay. So full rotation. So let's just write out what we know is true. Full rotation is every 24 hours. And any true statement can be written as a fractions. So 1 full rotation per 24-hour period. And we know equivalent to 1 full rotation is 360 degrees over that 24-hour period. And it's asking us, let's just make sure it says how many degrees. So we want it in degrees. So we're just going to take 360 and divide by 24 and find out that it looks like every hour we're rotating about 15 degrees. The next one I'd like to look at is number 77. So in your book, it says Earth's radius is approximately 3,900 miles. So let's just write out that's what we're reading here. The radius, I'm just going to draw a circle of the Earth. And the radius is 3,900 miles. Find the distance traveled by a low-flying bird and getting from a location at 40 degrees north latitude to a location at 20 degrees north latitude. If the bird flies due south, okay. So we're at, where is it at? We're at 40 degrees and we want to go to 20 degrees. Okay, so this is a 20-degree angle, right? And he's going to fly, and it says the bird flies due south. Okay, so let's figure out what we can do to solve this equation, what we've known so far. So one thing that we're going to make sure we introduce here is called our arc length. So our arc length is the measure of what we're traveling. We talked about that briefly when we talked about circumference and the radians. So radians is the arc length, and we can measure arc length by taking the radius of our circle and multiplying by our angle in radians. Okay, so our angle is 20 degrees. So we know that 20 degrees, if we multiply that by 2 pi over 360, or that's the same as 20 degrees times pi over 180, and we turn this into radians. This is pi over 9 is our angle. Okay, so our arc length that we're going to travel is going to be the radius, which is 3,900 times pi over 9. And so we can just divide the 3,900 divided by 9, 3,900 divided by 9, and we get 433.3 repeater pi miles is what we would have traveled. And the last problem that I would like to work on is number 81 from the book. So let's go and check that one out. On the next page, so 81 says here at the top, a bicycle with a tire radius of 18 inches travels at a speed of 20 miles per hour. What is the angular speed of the tires? Express your answers in both degrees per second and radians per second. So we want degrees per 1 second. I'm just going to write that down. And radians per 1 second, because they gave us information in miles per hour. So that's going to be important. So let's look at some formulas that we haven't introduced because it wasn't necessary quite yet. And that is our linear speed and angular speed. So let's just, I was deciding if I was going to show you in the book or on my paper here. So let's just go to right here. So at the bottom of page 408, it's talking about linear speed and angular speed. So it says an object that revolves about a fixed axis and at a fixed distance from it is said to be in circular motion, kind of like a bike tire, because it traces out a circular path as it revolves. The rate at which the angle is swept out per unit time is called the angular speed, usually expressed as the angle through which it rotates per unit time. If the angular speed is constant throughout the motion, the object is said to be in uniform circular motion. The distance traversed by the object per unit time is its linear speed. And it feels weird because it says speed, but it's the distance is the linear speed. So linear speed or distance is equal to the arc length S divided by time, where S is the arc length given by the radius times the angle in radians. The corresponding angular speed, which is using the Greek letter omega, is your angle divided by time, where your angle again, theta, is in radians. Okay, so because we can interchange your arc length with your radius times your angle, we can then go down here and write your linear speed in a couple different ways where my mouse is. Okay, linear speed of v, so the linear speed v of a point or that distance is the distance the radius r from the axis of motion is given by this. So it's the radius times your angular speed is your v. Okay, so the distance, your linear speed, let's go back and read that again. The distance traversed by the object per unit time is called your linear speed. So your linear speed, your distance of a point that is a distance r from the axis of rotation is given by this. Okay, so let's go back and look at number 81, and we're going to use some of this. Okay, so bicycle with a tire of radius 18 inches. So let's just write down R equals 18 inches. Travels at a speed of 20 miles per hour. So 20 miles per 1 hour. So we know they said, what is the angular speed of the tires? Express your answer in both degrees per second and radians per second. So we're going to have to get everything to seconds eventually anyway. Okay. So let's go to our paper here and see what information we have. So I know that we have the bike tire is a radius of 18, and I'm going to turn off the lights because it's so nice and bright outside. Oops. Okay. Okay, so we're traveling 20 miles an hour and we have our radius is 18. So we want to see we can see that we're traveling at 20 miles per hour and we have 18 inches as our radius. So thinking about this on our bike and we're traveling at 20 miles per hour. So we're moving around here 20 miles over every hour. Okay. So let's think about this and go back and look at our angles and then switch back to that. So we have to take in a couple things into account here because our radius is in inches and it's saying our linear speed is 20 miles in distance for every 1 hour traveled. We need to turn our miles into inches so that we've got our same units. So we're going to divide this by 1 mile and multiply by 5,280 feet. And then we're going to multiply by 12 inches and divide by 1 foot. So that will give us the number of inches we're traveling every hour. So 20 times 5,280 times 12. Okay, so we're actually traveling 1267200 inches every hour, but they want per second. So then that means 1 hour is 60 minutes and 1 minute is 60 seconds. So now we're going to divide by 60, divide by 60, and we're at 352 inches per second. Okay. So we're going to also use the formula that our linear speed is equal to our radius times our angular speed, the omega. And we want to solve for that. So we want our angular speed, which is going to be our linear speed divided by our radius. So that should be the 352 divided by the 18 to get 19.56. And then this is inches. So this should be 19.56 per second, revolutions per second, radians per second. Yes, because we're in angular, so this is radians per second. Okay, and then if we want to turn that into degrees, we can multiply that by pi, whoops, we can multiply that by 180 over pi. So 19, just exchange that. They wanted it in degrees as well. So we're going to take the 19.56 in radians and multiply by 180 and divide that by second, and so I can get my pi. And we have 1120.71 degrees. So here's our radians and here's our degrees, 1120. 1120.71. So we had to use our linear speed to get to our angular speed. And make sure you have units to units. That's important. So that wraps up chapter 5.1. There is a lot going on there. Don't hesitate to reach out if you want to have some tutoring time to go through some extra problems for practice. And we'll catch you back for 5.2. This is where things get exciting.